This is section 1.8, inverse relations and functions. So what we're going to talk about is what an inverse is, what do they look like, and how do you find one. So there are a few things that we need to get through. Shouldn't be too big of a deal, but this is something that you definitely have done before in Algebra 2. So we're going to use the horizontal line test to determine whether we have inverse functions, and we're going to find inverse functions algebraically and graphically. So let's talk about what an inverse relation looks like. So we have a definition here. It says that inverse relations exist if and only if a relation contains B comma A whenever the other relation contains A comma B. So what does that mean? Well, briefly, let's just talk about what that means. So if we have a relation here, and let's say we have these points 1 comma 2, 3 comma 4, and 5 comma 6, what that means is that if this is the original function, then it means that our inverse is just going to reverse our x's and our y's. 2 comma 1, 4 comma 3, and 6 comma 5. So this would be the inverse relation to what we have over on the left. Okay, real simple. We talk about switching x and y for inverse functions all the time, and this is just an example of how you would do that. Next thing is looking at a graph. So right here we have two functions that are inverses of each other. Okay, we are going to say that, you're being told that y equals plus or minus the square root of x is the inverse, and then this is the function. And what we find is when you look at it graphically, inverses are always reflections over the line y equals x. So if we kind of do a dotted line here, y equals x is the straight line that goes through the origin, kind of like that. And you can see that as we take our y equals x squared graph, you can kind of see that this portion right here reflects over the line to become this portion, and then this part of the line reflects over to be this part of the line. So that reflection shows that they are inverses of each other, and that will always be true if you have two functions that are inverses of each other. The next thing we want to talk about is something that is actually a function with it also being an inverse. So we're talking about inverse relations, but we have not said whether every inverse is a function. So what we need to do is we need to be able to determine whether something is an actual function or not, and we're going to do that if you look at the example we just did. So what we've typically done in the past is we've done something called the horizontal line test. So I'm going to create a line here. Let me see. I'm going to try and make it a different color here. Right. So what we do is, if we're going to look at this parabola over here, what we do is we try and pass the vertical line test, which says that it cannot go through more than one point. So as you can see, as I'm moving this line, you can see that our original graph is a function. So we know that the original graph is a function, but what about, this right here is a function. But what about our inverse? So if we do the inverse portion of it, you can see, you can see right away that this is not a function, and the reason is because it's going through more than one point. So what we would say is this right here is not a function. Now if I take that same line and I go to the one on the right, we're going to call this top line, this is the original. And again, if we take that line and we go back and forth with it, you can see that it does pass the vertical line test just on that line. Now if we go to the other line, that also passes the vertical line test. So because they both pass the vertical line test, if we say that this up here is the function, then this down here can be denoted as the inverse function. So if this is f of a up here, then this would be f inverse of a. So that little -1, that denotes what an inverse function is. Okay, so you can use the vertical line test once you have both functions graphed. Okay, so that's the vertical line test is something that we've used for a long time to determine whether something's a function or not. And really all we're looking for is, does it go through more than one point? So what we can also do is, first of all, we have to define that not all functions have inverse functions. They also have to pass the horizontal line test. So what we just did on the previous page was we talked about how they could pass the vertical line test. Well, there's actually a little bit easier way to determine whether an original function will actually have a inverse function. So what I'm going to do is I'm going to graph two graphs here. I'm going to do something that kind of looks like a cubic function. And then I'm going to put another function over here that looks like a parabolic or a quadratic function. And we're going to call these two different functions right now. So what we're going to do is we're going to use the horizontal line test. So this is the original function. So this is our f. And then this is our f. So if I were to do if I wanted to find out if the inverses are functions or not, I can now do something called the horizontal line test instead. Okay, so there's our horizontal line. And now let's check to see if this passes. So I'm going to take this, and as I go up this function, we are looking for the same thing as we would if it was a vertical line. Because it's a horizontal line test, all we're doing is determining whether it passes the test. And for this one, it does. So here, we could say that our function does have an inverse. And now when we do our parabola, we bring this over, and again, right away you should see that it's going through more than one point. So as soon as you see that it's going through more than one point, you would say does not have an inverse. And the reason why we can use the horizontal line test on the original function is because if you recall, we are going to be switching our x's and our y's. So if we switch our x's and our y's, it's like taking that vertical line test and it is changing it to a horizontal line test, because when you change your x's and y's, your verticals become horizontal and your horizontals become vertical. So we just use the original function and check for the horizontal line test. If we had both of them, we could just do the vertical line test on both of them, but because we don't have both of them, we do the horizontal line test just to check the original function for an inverse function. And we can do the same thing with this graph right here. So here, if we take our vertical line, or we're going to do a horizontal line test, and we're going to test. So y equals 4 over x. We take that horizontal line, we go up with it, and it does not go through more than one point of it. So that means we can say that y equals 4 over x has an inverse. Okay? So we can say, yes, there is an inverse. Okay, we do the same thing with the one on the right. We have an absolute value function, and again, right away you see that that horizontal line goes through two different points at a lot of different spots on the graph. So for this one, we'd say no inverse function. So that's how you determine graphically whether you have an inverse function. So now when we're going to start doing these algebraically. So it says if a function passes the horizontal line test, then it is said to be 1-to-1 because no x value is matched to more than one y value, and no y value is matched with more than one x value. Now that's not really that important to understand, but essentially we talk about how every x value has to have exactly one y value, and that's what's important. So now when we're going to find inverses algebraically, the first thing you want to check is to make sure that it actually has an inverse, meaning it has to pass the horizontal line test. The second step will be to switch your x and your y. So we've done this in the past, maybe in your Algebra 2 class, switching your x and your y, and then your third step is to solve for your new y. So let's look and see how this works. So we have the square root of x minus 4. So what we're going to do is if we were to graph this, you would see the graph look something like this. And if we were to do the horizontal line test, you would see that it passes it. So number 1, it passes. Okay, that's a terrible check mark, but that's okay. Okay, number 2, we're going to switch our x's and our y's. So it's going to be x equals the square root of y minus 4. And then our third step is going to be to solve for y. So to solve for y, what we would do is we would square both sides. So we'd end up with x squared equals y minus 4. Add 4 to both sides, and we end up with y equals x squared plus 4. And that's our inverse. Okay, so we switched our x's and our y's, and then we solve for y. The one on the right, this one is quite a bit more complicated, especially algebraically. We're going to skip over part 1. We're going to just say that it does have an inverse. If you were to graph it, you would see that. So we're just going to start algebraically in what we need to do. So we're going to switch our x's and our y's. So we're going to get x equals y minus 1 over x plus 2. Y plus 2. Switch all of our x's and our y's. So this becomes a little bit difficult because we have to isolate a y, and we've got a couple of them here, and you can't just cancel these out. So the first thing that we're going to do is we're going to eliminate the denominator. So we're going to multiply both sides by y plus 2. So what we will be left with is x times y plus 2 equals y minus 1. Still have y's on both sides, so we still have some issues. So let's multiply through here. So we're going to continue this by multiplying through. So we end up with xy plus 2x equals y minus 1. Now, if we're trying to isolate y, we need to get all of our y's on one side and anything that's not a y on the other side. So we're going to add 1 to both sides, and we're going to subtract xy to both sides. So that means we end up with 2x plus 1 on the left, and we end up with y minus xy on the right. So now what we can do is, because we only have y's on the right-hand side, we can factor out a y. So this will become y parentheses 1 minus x. So that's factoring a y off of each term. And then we can now divide both sides by 1 minus x. And we've now isolated y. Y equals 2x plus 1 over 1 minus x. That one is much more difficult. There's no question about that. So, and we'll work a little bit more with that. If you need to rewatch it. But it's definitely a skill that you need with a little bit more complicated problems. Okay, the last thing we're going to cover is using composition to find inverses, or to find out if there is an inverse. So, two functions are inverses if and only if. Basically, if you take the composition of functions, you take the f of g of x if it equals x, and then if you take g of f of x and it equals x. So basically, two functions are inverses of each other if you can take the composite in both directions and get x for each one. So let's see how this works with these two functions. We have 6 over x minus 4, and we have 6 divided by x plus 4. So the first thing we're going to do, we're going to do f of g of x. So f of g of x will be 6 over, and instead of x, I'm going to put in 6 over x plus 4 minus 4. Okay? So hopefully what you can see here is the 4's will cancel out. So now we are left with 6 over x. Now, if you remember how to divide fractions, what you do is you multiply by the reciprocal. So it'll be 6 over 1, that's this 6 right here, times the reciprocal of this, x over 6. You should then see that your 6's will cancel out, so we are left with just x. So that's done. Okay? Now, what I want you to do is, I want you to do it in the other direction. I want you to do g of f of x, and I want you to bring that to class, and I want you to see if you get x at the end to see if these are inverses of each other. So that's all I have. I will see you in class. Have a good night, day, whatever.